Hi, this week's mini test was done very well. And so I'm pretty happy with the class. You're working hard and you're getting the answers. Perhaps this first question was maybe the hardest one to work out because there's a whole number of steps. But we have an aldehyde and we've got a primary amine, so we're going to form an imine. And then because we're using a strong base like LHMDS, we're going to form the azaenolate. So this is going to be the point of attack over there, the nucleophilic carbon. Here's our electrophile, very good electrophile, alpha bromo ester. So this carbon is going to connect with that one, we have bromine leaving group, and then at the end we're going to get a hydrolysis. So the product of this is just, obviously the bromine in the starting material isn't going to react. This is an sp2 one. We're hydrolyzing back to the aldehyde, and we're going to have this messy here, OME. All right. So that's the product we get. Some of you hydrolyze the ester to the acid. That's fine. Esters are fairly difficult to hydrolyze with water and acid, but that's neither here nor there. I would have given you the marks for that. This one was a very simple question. It's a dicarbonyl species, very easy to deprotonate over there using a weak base such as sodium hydride, irreversible of course, forms the enolate, and then the only bromine that can react or is the leaving group is this one. This is not a good leaving group. This is an sp2 center. So the product of this was just the 1,3-dicarbonyl species again. Products. So we didn't do anything to the esters. We left them as is. Most of you actually recognize that, so there's no problem. Just as I mentioned to you before, always count your carbons and make sure that you don't lose anything on the way. There are 2 carbons over there, and we get that product over there. All right, so then the next question is just the formation, the kinetic enolate. We've got 2 positions over there. We're using a strong base, low temperature, sterically hindered base. So we're going to deprotonate over here. We're going to form the enolate on this side of the ketone, and we're going to use this as an alkylating agent. So a very boring alkylating agent. So the product, we've got the methyl group and we've got it on this side, and we just had to count the number of carbons and make sure that we kept it the same at 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 marks. Easy. And then finally, this was just the formation of the silyl enol ether. Easy stuff, nothing too hard about it. Make sure you know the mechanism of that. Remember, it's first this step. All right, we first get the silyl group going onto the oxygen. The second step, part 2, is where the base picks up the proton. It's a thermodynamic process. So the product is the thermodynamic enol ether, double bond, TMS, and that was very well done. And the last thing is, remember what we learned in class is that we can take that TMS group off. One of the easiest ways of doing that is with methyl lithium, and the Me minus picks up the TMS group, and we end up with an O minus, and it's a way of generating enolates from silyl enol ethers. So yeah, that's the answer for that weekly test. Good luck.